Very good, big welcome to Sam, who's going to give us a talk on the Iceni 70 SEMS transverter that he's been developing. Sam's been a pretty good supporter of the constructing side of the hobby. Unfortunately, I think 70 SEMS still is a little bit of a hotbed of home construction. So hopefully he'll be able to detail that with his lecture. So there you go, Sam. Take it away. Thank you very much.
Thank you, Richard. Before I start, this is Richard's fault. Several years ago, he did a talk here on promoting 70 SEM activity. At that time, I'd been playing around with the 2-meter transverter design. His prompting to do something about 70 centimeters was probably as responsible as anything else for the Iceni transverter coming into being. There was one other person I have to blame as well, and that was VK4OE, who kept hounding me, when are you going to do a 70 SEM transverter? And he hasn't bought one. If you're viewing the video, okay, let me just see where the down arrow is on this. Iceni is the name of a tribe who lived in the north part of East Anglia 2,000 years ago. The most famous member of whom is probably, is Boudica or Boadicea, however you want to pronounce it. And they were probably responsible for the very first Brexit because they tried to drive out the Romans. There was a Roman treaty and the Romans came here. They tried to drive them out. The other little thing about it that relates to the Iceni is they always used to go into battle dressed in blue woad. Note the colour of the printed circuit board. That's not really photoresist, that's war paint. Iceni is relatively simple to construct 70 centimetre transverter. There's still a lot of people who want transverters. I would think pretty much everybody in this room has probably got an HF rig. They're aspiring to or have an SDR transceiver as well. But if you've got an HF rig that covers 10 meters that you like using, that you're familiar with, and you want to get onto 70 centimeters, this is one way to do it. Iceni then was designed to be a simple to build transverter. There are some little parts of it which are maybe slightly more complicated than others, but it's fairly simple, it's very reliable. I've produced many, many kits for Iceni now, and I don't think anybody's had any real problems with them. We can't sort out in a matter of a few minutes or so. What I'm going to put into the talk is maybe that's the next slide. This is the performance of Iceni. On receive, better than a 1.5 dB noise figure. You're probably going to use it with a masthead preamplifier, so the noise figure of the transverter receive side is not that critical. Nominally 24 dB of gain on the receive path. Something which has changed recently is the dynamic range. I'm using a new mixer, and minus 1 dB typical, 1 dBm input third order intercept is pretty good. Most of you won't have a radio that probably by the time you've stuck the gain of this behind it can cope with this. This will be working when your radio has collapsed. On transmit, the module itself produces plus 17 dBm out, 50 milliwatts. Third order IMD is a neg 40 dBc, or neg 46 with respect to PEP, and the transmit gain is 17 dB. And most important these days, it can be frequency locked, and I will explain that to you afterwards. This is the general block diagram, and if you've ever built your own transverter or looked at transverters, the block diagram will be completely familiar to you. If we look at the receive side first, Receive signals at 432 from your antenna pass through an RF amplifier. They pass through a bandpass filter into a bilateral mixer, that is one which is used on transmit and receive, down into a post-mixer amplifier and a bandpass filter. The bandpass filter at the IF is designed to keep any other unwanted products out of your radio so it doesn't cause problems. On transmit, the 28 megahertz input goes through a variable attenuator, so you can set the drive level anything from 0 dBm down by about 15 dB. There's some pin switching and that in here, and a diplexer, which I've not put on the block diagram, into the mixer through the same helical filter, into the transmit amplifier chain, which is two-stage and which has yet another filter in order to clean up the output spectrum. And there is a low-pass filter on the output. But that's a fairly typical block diagram. There is a local oscillator, of course. The local oscillator runs at 101 megahertz. It's typically, as you would expect, a Butler oscillator coming from me. It's a two-stage Butler oscillator, very much refined after Leaf SM5 BSZ did some work on the Butler oscillator that I had in the Anglian, came up with some really good suggestions which improved the performance quite dramatically in terms of phase noise. So I've used that design into the local oscillator multiplier to 404 megahertz and then driving the mixer. And of course there is some control circuitry up here for transmit receive switching, there's a couple of little LEDs on the board that show you when it's transmit or receive. There's actually a little sequencer built into there, and it works just from a press to talk input. I have abandoned the idea of putting plus 12 volts at high impedance up the coax to switch it to transmit. Nobody seemed to want that from a 28 megahertz IF drive. Don't worry that you can't read that. I can't read it from here. You'll probably be struggling from there. We're not going to do very much with it, but that's the circuit diagram of the Iceni. And just for reference, there's a high definition version of that on my web page, so you can, if you want to look at the circuit in more detail, just go on the web page and download the schematic. It's on a PDF. The Iceni is built on a printed circuit board. It's 62 by 100 millimeters. There's the board. I'll pass this round. It is surface mount construction, and it's designed, as you'll see in a moment, to go into a particular size freely available tin plate box, or if I've included the photograph, I've got another alternative you can put it in now as well. There are a couple of minor errors on that board, but until I've got rid of the stock of those ones, I'm not going to do the revised board. They're fairly minor things, which is easy to sort out. I ought to point this out that I use mainly for passives 0805 size SMD. If you use a magnifying headset, pair of tweezers and a suitable size soldering iron, they're very easy to work with. Some of my preamplifiers use 0603 size. They're getting to be a bit more of a challenge. These are fairly easy to work with. This is what the transverter looks like. This is an assembled board before it goes into the box. You can see these helical filters. When I was designing this, I had a big debate about what I should use for the filtering. These are Toco filters. They're no longer made, but Franco in Italy has quite large stocks of this particular one. It's not actually designed for 432. It has a center frequency of 450, but my tests on a vector network analyzer show that the input return loss is quite acceptable when they're tuned down to 432, and they will tune quite happily to 432 as a center frequency. They're not the cheapest filters in the world. They are surface mount, and I'll be talking about that in a little more detail in a moment. surface mount, so you've got these pins that you have to make connection on the board. And that's probably the most awkward part of the construction. It's not difficult, it's just that you've got to be careful when you're making the connections. And just a view of the top of the board with a couple of comments. When the board is in a box, the crystal is on the top of the board. There's a coil at the input. There's a heat sink over here. There's a voltage regulator underneath the board, and that just helps to get rid of a bit more of the heat. I did try the other day when I built one of these to solder this copper heat sink to the tin plate box. I gave up after a while. It was just hopeless. It's a self-adhesive mini heat sink, which are sold as heat sinks for Raspberry Pis. The comment about this is that this is a Toco coil. These are no longer made. They haven't been made for many, many years. I had a stack of them, so I used them in the first few transverters. I wasn't expecting to be making many of these. And then I ran out, so there's an option of using an air-wound coil. And then a few weeks ago, I came across another small stack of them. So I'm being back to using. They're actually much easier to adjust than stretching out a coil trying to get the noise figure to its lowest. So you've got one of those. The crystal here is shown without any form of heating in that, but you can slip a crystal heater over it, either a posistor, a 40-degree one, don't put the 60 on it. They're crystallic crystals. They are cut for room temperature. They're quite happy at 40 degrees. At 60, they're beginning to complain. Alternatively, you can put one of the DB6, the Kuna crystal heaters on there, the QH40s, they're 40-degree heaters, and that'll fit on there quite nicely. You can pick up your 12-volt supply from here, ground the other end of it, and that helps to maintain the stability until you're going to do the other frequency locking mod, which I will describe. This is Iceni in its case. Here's one I built earlier. And again, I'll pass this around. One thing you will notice immediately is that there's a little cut and strap on the board. I'll explain what that is in a moment, but you want to take a look. Don't put your fingers inside, please. I hate to have to go back and retune it again. Excuse us, this thing keeps feeling like it's falling off my head. This is an alternative way of housing the transverter. This is a Hammond 1455. The box that I got surplus and it had plastic end cheeks. If you substitute an N for that J, then you'll get the one with aluminium end plates, and that's far better. But I've got a couple of these, so I guillotined a couple of end panels for it. But the board just fits in there beautiful. It's exactly the size of that. It doesn't slide in. It sits flat on the floor of the box. In fact, stood off on an M2.5 nut with a screw through the bottom of the box. These three are edge connectors. You can carefully drill the panels so that those three stick through. If you use the extended thread SMAs, then you can fix it in place by doing up the nuts on them. This end, there's a very convenient gap because now you can bring a short coax off the two coaxial connections there, and if you put on the back here, your SMAs are only running at 28 megahertz, so you can panel mount ones on there and connect them to these points. And above that, you can have phono sockets for the interfaces for PTT, for earth on, transmit out, and so on, and some sort of power socket for getting 12 volts into it. But that's a really convenient, neat way of doing it, and I forgot to bring one to show you. Somebody was asking me earlier on about this situation. When this was designed, Avago was still Avago. Since it was designed, Broadcom have bought Avago and promptly discontinued the vast majority of the Avago range of mimics and devices. So, for example, John was saying in his talk this morning about using the ATF 53889, whatever it was. You can't get it anymore. Unless you want to buy 10,000, they'll run those off for you on a fab, but and you'll find some surplus. Fortunately, and fairly quickly, Mini Circuit said, we've got replacements for those. They use different fabs around the world, as far as I can make out, and they do have equivalents. So one of the devices that I was very keen on, the MGA 30689, which is a little SOT89 mimic, which is virtually unbustable unless you stick 10 watts up the back end of it, and a few people have. That's now been replaced by the PGA 105 Plus, and please note 105 Plus, not the 103 Plus. It sits there with about a 2.5 dB noise figure at 10 meters on the IF, has a third order output intercept somewhere around about 20 watts. It's quite an incredible little device. And also as a result of the work that Leaf did last year on the lower level mimics, we had an SPF 5043 originally. Leaf identified that those devices have actually got a bias circuit problem as far as we can determine, because the amplitude noise, not the noise figure, but the amplitude noise when these are used in a circuit where it's been subjected to a high level signal, you get very high levels of reciprocal mixing problems with it. He had already been using PSA 4 5043s, again from Mini Circuits. These don't seem to suffer that problem at all, so those are the preferred replacement devices for the lower level stages. Now, a change that I made a little bit earlier this year, I was looking, one of the reasons I made a start on the Iceni one I did was that I was given a small batch of ADE 13 wideband mixers. Now these are 1600 megahertz parts. To use them at 432, it's right in the middle of their range geometrically. It's the right sort of device and frequency range to use, but they're only level 7 mixers. That means they wanted plus 7 dBm local oscillators. So the dynamic range, not that brilliant, but the local oscillator to RF port isolation on those devices, really good. So any LO that fed through into the transmit chain virtually wasn't any. Ideal for a transverter of this sort. But there are no pin compatible high level mixers for the ADE 13. It doesn't exist. The nearest is an ADE 751, which is in the same package, but the IF and RF ports are reversed. Well, I got hold of some of those and I put them into the circuit without making any changes, and it was a disaster area. It really was awful. There was no isolation between LO to RF on it, so I put them on the shelf. And then one of the German amateurs said to me, "Have you tried a different mixer?" And I said, "Well, I've tried these 751s, but they don't work and that." He said, "Yeah, I was looking at those, but you need to reverse the ports." I said, "Well, if you want to do that, let me know how you get on." Yeah, he said. So I sent him one of the samples that I had, and he reported back a dramatic improvement in the dynamic range, and none of this problem with the LO to RF isolation. And then, completely out of the blue, one of the OKs who works at Prague University came up with pretty much the same question. "Have you tried an ADE 751? "No, but here's one if you'd like to have a go." And again, he did a full set of measurements and came back and said, "Yeah, these are really good." And he was reporting a dramatic improvement in the dynamic range. The input third order intercept had gone up quite dramatically. So I thought, I better try this as well. So I tried it, and sure enough, if you change those two pins over, which you have to do with a cut and strap arrangement, which I'll show you in a moment, then you do get a dramatic improvement. The one thing which it didn't do was it wasn't as good on the local oscillator to RF isolation, so that on transmit there was slightly higher level of 404 meg feed through to the output. That bothered me quite a bit. By the way, that's a level 13 mixer, and in this transverter, although this is level 7, I was actually driving with plus 13 on the basis that most mixers work a lot better when you drive them a bit harder. You drive them fully into switch mode. It doesn't work with the ADA 13. Oh. But the isolation wasn't quite as good. But I was building one of these the other day for somebody, and I thought, I wonder, and I seam soldered the filter, both filters, the helical filters, rather than just soldering the pins. I seam soldered it in, and the LO to RF isolation went down to the same as it was on the 13. So I no longer have that as a concern. So when people have been buying these kits off me, that's the device I've been supplying. This is the upgrade or bodge. I'm not going to get any more boards done until I've got rid of a few more of the boards that I've got at the moment, but I will produce some new boards. So basically, here's your mixer. You have to cut two tracks. The RF one that went to the filter, you cut there. The IF one, which went down here, you cut there. You put a very short wire strap across here, which is this. You use a very short length of mini coaxial cable, and if you have one of the kits, or you have a mixer upgrade of that, I supply some very thin coax, which you then tin. You take the jacket off it, tin it, and that goes between that pin, the RF port on the mixer, and round to the filter input, and you ground it to some of these vias in a few places. So I won't say, as you'll see when that one goes round, I wouldn't say it's the neatest job in the world, but it does the work. And I've seen many, many commercial, professional boards where there's been cut and strapping going on. It's not that unusual. Now, when you've built your transverter, this gets a little bit out of step. I thought I would talk about alignment and test before I talk about some of the measurements. There's certain test gear you really want access to. You really ought to have access to a spectrum analyzer. Nobody should be building radio equipment, even as radio amateurs, are not at least putting it on a spectrum analyzer somewhere and checking it's doing what you think it's doing. And if you buy one of the little RF Explorer signal generators, for example, they're quite adequate for doing this sort of check. It's nice to have a signal generator, a calibrated one, at least calibrated in terms that when you say you want neg 10 out or neg 20 out, that's the level you will get. That covers both 28 megahertz for when you're doing the transmitter test and 432 megahertz when you're doing the receiver test. Again, the little seed signal generator does the trick, but you're probably going to have to put an external attenuator on there to get the levels that you want, because the steps that it provides are a bit coarse. And you'll need a test probe, because it won't work the first time you put it together. There'll be something that won't work. I published in my microwave column many years ago a couple of probes, but one of the probes which I highly recommend, so you can signal trace. So when you set this transverter up and you put you go on to transmit and you put your 0 dBm in and nothing comes out, where's the signal gone? Now, you don't go dabbing a 50 ohm test lead onto these various parts of the circuit, because you'll get some very misleading readings. What you need is a probe. And in the best Blue Peter tradition, here's one I made earlier. That's a piece of 50 ohm coax, and on the end of it, in series with it, there is a 510 ohm resistor. It should be a 500 ohm, but 510 ohm resistor because it's the nearest preferred value. Now, when you put this into your spectrum analyzer, within a 50 ohm point in the circuit, and most of the test points in the circuit are nominally 50 ohm, you put this in there and you'll get a reading which will be 20 dB nominally below the actual level at that point. It's a neg 20 dB passive probe, plus or minus a couple of dB, but we're trying to find out where the signal's disappeared to, so it's going to be pretty gross. You'll know when it's disappeared. Simple, and everybody ought to have one of these. I've taken an old SMA, I've taken the sleeve off it as a crimp one, and I put that over the resistor, and I've put the pin, the gold-plated pin, on the other end of the resistor to use on the probe. I'll show you another slide in a moment. But if you take nothing else away from this talk, make yourself a probe. If you do any test equipment, if you do any tests on equipment, you need a probe. And that'll be good up until several gigahertz. It's mainly capacitive, but having that gold-plated sleeve on there, you're holding it, it's quite adequate. You don't need to put an earth lead on. These are what I actually use. These you'll recognize as coming on certain types of scope. They come in different resistance values, but a 500 ohm in a 50 ohm system gives you your 20 dB. It's got an SMC connector on it, so I put an SMC to SMC back to back into an SMA lead. Does the trick beautifully. This is what it looks like when it's all screwed together. But this is the homemade one. Here's your coax, little sleeve, and the sleeve's not absolutely necessary. If you can grab hold of the tinned braid, that's quite adequate. And just to make sure you make a good contact, so I've used the pin off an SMA plug, and that does the job beautifully. So it's a 20 dB probe. And basically, that's what it looks like. It goes onto the 50 ohm input in your spectrum analyzer. Now you can look at signal levels, and because you're using the spectrum analyzer, rather than a power meter or something, you're looking at the signal level at the frequency that you want to look at, and not some spurious signal or whatever. It's a selective power meter. Okay, so now you've used your probe and your test equipment and your Iceni's up and running. Let's do a few quick measurements. This is the measurement of the receive side dynamic range. I've got two signal generators which I can use. One is a Roden-Schwarz SMG, relatively low phase noise, about neg 142 dBc at 432 at 10 kilohertz offset, and this is a British-made Marconi, which is fairly reasonable. I combine these two in a mini circuit ZFR SC. That's a 6 dB combiner, very low intermod. Then into a TechScan variable step attenuator. Now this is two tones. At this point, each tone is neg 40 dBm. That's about the right sort of test level for this, because it's possible if you use two higher levels to give yourself a very misleading reading. So here we go, and you can't actually see the level of third order coming out of this. That combiner, and that is so good. You calibrate up the system around your Iceni. Here's your spectrum analyzer set at 28 megahertz. I've got an 8592. Again, at neg 40 in, you're looking for products down here which are around neg 80 dBm. That's pretty low level. So all of this is getting sort of, was it, wasn't it? And you've got to make sure that this is clean, otherwise you're going to get some really strange readings. So putting this in, connect up the Iceni, measure the level of each tone at the output. You see here, this has got 24 dB of gain, neg 40 per tone, neg 16 per tone at the output. Nice and clean, no third order. In fact, you can just see them in there. And that was taken with the ADE13. With the ADE751 mixer, these just totally disappear altogether with the dynamic range I have available. So my neg 1 dBm measurement of third order input intercept is probably a little pessimistic, but it's the same order of measurement that our friends in Prague made, so okay. So that's measuring the receive side dynamic range. I use AppCAD a lot, and here I've plugged in these numbers. So forget that for the moment, because that's the result. Here we're going in at neg 35 dBm per tone, 24 dB of gain, the level of the product there at neg 79. This calculates it for us, providing we tick the appropriate boxes here, and we find we've got an IIP3 of neg 1 dBm. So it's a very convenient way of calculating what the third order intercept is. There's a lot of other useful information on there as well, but for the moment we won't bother with that. And I'm not going to labour this too much, but these are the measurements that were made on the prototype Iceni with the 751, measuring at the 28 meg IF output, but obviously I'm measuring the noise at 432 input. It says that the insertion gain, excuse me for a moment while I readjust. So 28 meg IF, I'm seeing 24.41 for this particular one as the insertion gain, and a noise figure of 1.27 dB, which is very respectable. I nominally claim better than neg 1.1. Now with the ADE 13, this was up around about 1.8, 1.9 dB, in fact 2 dB in some instances. Have a little look at what's going on inside the box. Now we know what to measure it. On the transmit side, an input attenuator, it's a fairly crude L-pad. Then there's a 28 meg bandpass filter, because a lot of the HF rigs that we use, if you look at the 28 meg IF output, they're not exactly clean. That's not going to clean up anything very close in, but if you've got something coming out at 35 megahertz, for example, when you wanted 28, and you've got this quite high level 35, and I'm thinking here IC735s, which were notorious for that. A diode switch, BAP64s, pin switch, a little diplexer, into the mixer, bandpass filter, another pin switch on the output side of the filter, transmit amplifier, another bandpass filter, another transmit amplifier, and then a low pass filter on the output. Now because it's a low power module and it's going to be connected to something else, I haven't gone to town on the low pass filtering, it's only a single section low pass filter. Here's the local oscillator just as a block, plus 13 in. It develops that fairly easily. There's no big dramas in setting that output level. Here's the nominal levels. So remember, this is 17 dB gain max on transmit. A lot of people have asked me, what output should I be getting? Well, where's your attenuator set? What are you putting in? It's 17 dB. It's no different to on transmit. If you've got 17 dB of gain, you've got 17 dB of gain. There will be a maximum you can put in, but if you put in 0 dB, which is my recommended level with the ADE 751, so 0 there will go in there at notionally neg 3 dBm, neg 10 coming out. It does measure about 7 dB of conversion gain, conversion loss. By the time you come through the bandpass filter and diode switch, you're down to neg 15. Because these helical filters were never made for 432 megahertz, their insertion loss is slightly higher than you would really like. Diode switch, transmit amplifier, out that first stage plus 9, another bandpass filter, so the level drops down again. PGA 105 at the output, low pass filter, plus 17 out. It's a linear transverter. If you put in neg 6, this will be 6 dB lower. If you put in plus 3, this will go to plus 20, but it's just starting to saturate because this stage is running into saturation. Okay? Okay. Just have a look at the spectrum. This is the spectrum from 10 megahertz to 1.5 G. That's the wanted carrier. That's the second harmonic. As I said, there's only a single stage of low-pass filtering. Apologies for this. I used a K3 two-tone drive, but the resolution bandwidth on my spectrum analyzer is not good enough to really separate out the tones, but the third order and transmit is about 40 dB down. Local oscillator, I'm not going to labour this. 101 meg Butler oscillator, local oscillator amplifier. That must be written on the board behind. You can lock the Iceni. There's a socket on it marked external LO input. You can take it as an output as well, but as an LO input. If you, this seems to be the easiest way at the moment. This is a Leo Bodnar Mini GPS. Set that to 101 megahertz. No more than 0 dBm. I'm not going to go into all the injection locking theory at the moment, but essentially the lower you can get away with, the better. But if you set that notionally to 0 dBm at 101 megahertz, and you stick a GPS antenna on the other port to lock it, you've now GPS discipline locked your Iceni on frequency. If you're doing digital FT8 or whatever, it's nice to know exactly what frequency you're on. You leave a crystal in there. That was the idea of leaving that there, just to show the crystal stays there. That question has been asked a number of times. The crystal stays in place. You are injection locking. It's a first order phased lock loop, I am told. And here's the proof that it's injection locking in phase. 2 signal generators set to 101 megahertz. Sorry, one set to 101. Its output is split and fed into 2 separate Iceni transverters, the IF output of which go to 2 channels on a scope. So this is 28 megahertz this is looking at. We inject the same signal, 432.2, at the input at appropriate level and split it and feed it into both Icenis. And we see at the output that these are locked in phase. There's a phase difference between them, but that's purely path length or whatever. If you're going to use this for diversity and you really want these to be absolutely in phase, you can usually adjust it in the software, or you can, or on the IF output of one of these, you can stick a short length of coax or whatever, if you really must want them absolutely in phase. But this can be used for diversity reception. One of these can be a full Iceni, the other one can be the receive-only part of one. Very useful for EMI on 70 centimeters, where you want to look for, whether you've got a horizontal and a vertical array, and you can look at the 2 signals and put them into whatever SDR is currently being specified to be used for that. And there is that locked waveform you saw just now. It does work. And it works because when you injection lock, what you're doing is you're injecting current into the oscillator in a particular phase. The oscillator will stop unless it can adjust its phase to be in line with the phase of the signal you're feeding in. So it is phase locked to it. Can't do anything else. And it works incredibly reliably. The downside to it is that if you use a noisy reference to feed into it, garbage in, garbage out. So you want the best you can inject at the 101 frequency, the lowest phase noise. I'm trying to get some measurements done by Leo Bodnar at the moment for this. Leo's assisting me with this, and we should, I hope, have some definitive numbers fairly soon. Just to show you that my shack can be as big a mess as anybody else's. Here are the two Icenis. Here are the ZFSR, the splitters. The spectrum analyzer, one of the two signal generators, and the scope's over here somewhere. That's what he looks like. That bench is only marginally cleaner now than it was when this photograph was taken. And that's it. If you need more information, have a look at my webpage. You'll find a full set of instructions. If you want to do your own thing, all the information is there that you need. Quite happy to let you have a board if you want to build your own. And that's it.
Fantastic, Sam. Thank you very much indeed. Right, time for a couple of questions. Anybody? So, your name and your course, sir.
Sorry, yeah. Sensor G7B3. Got a Leo Bodnar. For me, as a rank amateur, it's a fairly horrible waveform. The 50 load. Does that matter?
No. No. In fact, I deliberately inject, even at 404 further down the chain, a dirty waveform. Ideally, it should be a square wave for good switching of the mixer. It's not actually that. If you look at the waveform, if you look at the spectrum at 404, it looks pretty awful, but it's actually causing no problem, and it is increasing the dynamic range by switching the mixer. So don't get too worried about that. What you might get more worried about is if the source you're injecting has got some unwanted spurious in there at, say, 10 kilohertz off or whatever. That might be a concern. But the waveform, it's a sine wave it produces, a notional sine wave from a CMOS driver into 50 ohms.
As long as the fundamental's okay, that's good enough.
Absolutely.
Thank you.
Right. Time for one more. Anyone, please? No?
Can I ask a question?
Yes, sir.
Where's my bits?
Somebody's just got after them, haven't they? Right, thank you very much, Sam. Thank you.